Cool. Yeah, okay. Hi, everyone. I'm Andrew. I'm a postdoc at the Institute of Cosmology and Gravitation at the University of Portsmouth. But today I'm going to be telling you about some recently published work from the end of my PhD at the University of Sussex on primordial black holes and how much we can get information about the power spectrum from them. So first, I'll give you a brief introduction to what PBHs are. Then I'll talk about the mass distribution for them and how we can use that to constrain the power spectrum. And finally, I'll conclude. So first, a brief introduction to primordial black holes. The first question on your mind is probably, well, what is a primordial black hole? So a PBH is a black hole formed from inflationary perturbations in the early universe. So during inflation, we have quantum fluctuations, and these get expanded by the fast acceleration into physical overdensities. We characterize these overdensities with the density contrast delta, or more carefully, we use something called the compaction function C. And after inflation, typically during radiation domination, if at horizon re-entry, this compaction is greater than a certain critical value, then we form a primordial black hole. So the next question you're wondering is, why should we care about these objects? What are they useful for? So firstly, they're very different to astrophysical black holes. So one key difference is, while an astrophysical black hole, you could never get one that's subsolar mass, primordial black holes have no limitation on their mass because they form before baryogenesis, so there's no pressure. So you could easily get a subsolar mass primordial black hole. You can even go down as small as 10 to the 15 grams, and those are ones that would be evaporating right now. So that's one thing they're interesting for. Secondly, they're a potential dark matter candidate without requiring physics beyond the standard model. And we characterize this through a parameter called FPBH, which is the fraction of dark matter in the form of primordial black holes. Then there's a question about whether they could be the seeds of supermassive black holes and be important for galaxy formation. I won't touch on this in this talk, but it's another interesting avenue to look at. Not finally, but again, recently there's been a lot of activity with the LVK merger events, so the LIGO-Virgo-Cagra collaboration, and I'll talk about these in a bit more detail just now. And finally, because they are objects in the early universe, we can use them to constrain the physics of the early universe. And crucially, they're small-scale objects, so we can constrain the small-scale physics well away from the larger scales we have constraints from the CMB on. So the LVK detection. So LIGO-Virgo-Cagra have detected a number of binary black hole mergers. There's now 3 observing runs of detections that have been released, and these have some curious properties. So 2 of these I'll highlight. One is the low effective spin. So this is a parameter that couples the intrinsic spin of the black holes to their orbital angular momentum. And many of the events LIGO sees have this parameter being very low. So there's some ways you could make this work, but the easiest way is to make the intrinsic spin low. And for primordial black holes, we do expect them to form with low intrinsic spin, whereas astrophysically, we might not expect this. Secondly, there's the mass gaps. So astrophysical black holes, you'd expect to form with these 2 mass gaps in their distribution, one between 2 to 5 solar masses or so, between the heaviest neutron star and the lightest black hole, and one up about 50 to 100 solar masses due to the pair instability process. However, LIGO-LVK have seen objects in both of these mass gaps. So the easiest explanation without introducing exotic objects such as primordial black holes is to say these could be hierarchical mergers. So they're the results of previous merger events that now make an object that's merging again, and that object is in the mass gap. Obviously, it also could be a motivation for saying these objects could be primordial because they have no restriction on the masses. What we know is that the mass distribution is absolutely critical. So you need to know the mass distribution really well to be able to describe all of these late universe observables correctly. So now let's talk about that mass distribution and how we actually form primordial black holes. So first, to get primordial black holes, you need a peak in the power spectrum. Here we're talking about primordial black holes formed from inflationary perturbations. You could get other methods such as reheating can do something, or cosmic strings, but we're going to ignore those and talk about just inflation. So you need a peak. You need to grow from this 10 to the minus 9 CMB value all the way up to 10 to the minus 3 or 10 to the minus 2. For this, we take a log normal. It has parameters amplitude A, the peak position KP, and the width delta. And we normalize it appropriately such that integrating over log K gives the amplitude A, and we do this such that it matches a delta function in the limit of the width tending to 0. Secondly, when calculating the mass distribution, you need to take into account critical collapse. So we heard a little bit about this sort of scaling, and again here we're seeing exactly the same thing. So M goes as the compaction minus the critical value to some power, and this power in fact is 0.36 or 0.37 as we heard earlier. And this is important because it means that even a delta function, even a monochromatic power spectrum, you cannot get a monochromatic mass distribution. It always gives you an extended mass distribution. So let's look at what this mass distribution looks like. And particularly, we're interested in quite narrow power spectra. So on the left here, we've got a range of power spectra with a width from 0, the delta function, all the way up to 0.3. And you can see that it looks very different. On the right, we've got the corresponding mass distributions. And you can see that they don't look very different. So this is an important conclusion and one I'll come back to in a second. But first, if we look at the shape on the right, a lot of the time when people move beyond monochromatic mass distributions, they go straight to a log normal, which is a Gaussian defined in log space. And this is a very commonly used assumption for what the mass distribution might look like. But as you can see, looking at this plot, this is a numerical calculation. It's very much not Gaussian. It's not symmetric in log space. So it can't be log normal. It's really showing quite significant deviations. And this has been known for a while, since the late 90s, but it's sort of overlooked sometimes. So what we did, we considered a range of possible models that may fit better over a whole range of power spectrum widths. And you can see actually for the monochromatic power spectrum, the delta function right on the left, the log normal is actually the worst model we considered. It even does less well than just a straight Gaussian. However, it starts to improve a lot more over some of the models as you tend to larger widths. But across the entire range, you can see these two models, the skew log normal, which is a skewed Gaussian defined in log space, and CC3, which is a critically collapsed motivated model, but what it boils down to is a power law on the rising slope and an exponential on the falling slope, and the two slopes are independent. You can see that those two do significantly better than the log normal across basically the entire range of widths. There is a price to pay. They are 3-parameter models, whereas the log normal is only a 2-parameter model, but it really does provide a significant improvement over the log normal to fit the actual mass distribution, especially at these lower widths. And you can see this is important. So going back to this plot on the right, this very asymmetric tail on the left, for example, the constraints we put on primordial black holes, sometimes they go very, very quickly. So evaporation constraints go from FPBH of 1, so all of dark matter is primordial black holes, to FPBH of essentially 0 in a very small range of masses. And if you put the mass distribution as log normal and put that up next to your FPBH constraints, you would say, well, actually it fits fine. We avoid these constraints. But if you have this very asymmetric tail, suddenly you're not avoiding these constraints. Problem. So you really want to make sure you're modeling this correctly. Now, the other point I mentioned earlier, on the left, you can see a wide diversity in the range of the power spectra and the width of the power spectrum particularly. But on the right, there's almost no difference in the mass distribution. And this is because when you get to narrow enough power spectra, the effects of critical collapse really drive the distribution. It drives the shape of the distribution, and to the point that the power spectrum shape is essentially neglected. I could swap out this log normal for a power law or a Gaussian or anything else. You would not see it really in the mass distribution. You wouldn't see anything at all. And so even a very precise measurement of the mass distribution may not be able to tell us much about the power spectrum that formed them. With a caveat, everything I've talked about so far is for Gaussian perturbations. So what about non-Gaussianity? Well, non-Gaussianity enhances the probability of large perturbations if we choose it in the right direction. So it may enhance the probability of large compactions. We know that this corresponds to large masses, so that would lead us to a high mass tail enhancement. But we want to know how this works properly. Stochastic inflation, which is a non-perturbative mechanism, generically predicts non-Gaussianity, typically with an exponential tail. But you need to be careful and make sure you've got a fully non-perturbative treatment of how the effect on P of zeta goes through to the compaction and hence the mass distribution. And that's what I'm working on now in my postdoc at the ICG. So that brings me to my conclusions, which I'll go over a little bit quickly because I've run out of time. So first, I hope I've made it clear that the mass distribution for primordial black holes is as important as their total abundance, if not more so. It's vital to take into account critical collapse. And when you do so, you see that it's not log normal, and you need to potentially come up with a better model, such as the skew log normal or this critical collapse model, to work with future accurate data. And even very precise measurements of the mass distribution might not be able to provide full information on the power spectrum, but they could probe non-Gaussianity.